Okay, good morning, everyone. So my name is Juliane Reinecke. I'm a professor of management studies and faculty director for sustainability. You might have seen me at the debate last week, which was a lot of fun. So today I'm really pleased to welcome you to the second edition of our MBA Climate Bootcamp. And I think that's a really special moment for us here, because as you stand at the threshold of your MBA journey and you're stepping into a world that is rapidly evolving, and we're in the midst of not just one crisis, but many profound crises. And the one we want to focus on today is the climate crisis that is really reshaping our planet and threatening the very systems that our lives and businesses really depend on. And I think it's not just a problem for anyone else to solve. It's really a challenge. It's really a leadership's challenge. So for those who aspire to lead, and that's you, that's our new class of MBA students coming in their second week of launch here at Oxford. And so, you will find yourself at the forefront of this challenge. And so we want you to be able to, confront this challenge with a sense of, climate literacy, that what is, some of the science behind, what is the policy, what are the challenges from a business perspective, the strategic challenge, operational, technological challenges that are involved. And we want you to step up with confidence and become leaders who can confront this challenge and contribute positively to it. So here at Oxford, we're very privileged that we're part of a larger university where we have the world-leading experts who are really at the forefront of the science, exploring different aspects of climate change, economics, policy, and beyond. And so today, as part of this bootcamp, you will really hear from these experts today to really deepen your understanding. Because the insights to tackle this doesn't come from just one discipline, but through the collaboration of many. So just to give you a little bit of idea of what's happening today, so we kick off this bootcamp with Professor Myles, who I'm going to just introduce in a second, a leading climate scientist here at the university. And then you will break off into 4 different cohorts, where you had some choices to hear from 4 of our other experts. And I must really say, this was really the dream team that I put together. These are really kind of scholars who I deeply respect and who I really look forward to hearing what their latest research is. And that's Dr. Mary Johnstone-Lewis, who's a senior fellow in management practice here at the Saïd Business School, and who's leading the Oxford Sustainable Business Program. And with her co-director Alexis McGivern, who is the head of stakeholder engagement and research fellow at Oxford Net Zero. Then there will be Dr. Jimmy Jha, who just completed his doctorate on carbon accounting, and who will share some of his research insights with you. We have Dr. Benjamin Franter, who is associate professor of climate litigation and the head of the climate litigation lab. So these will be 2 sessions, and those who you don't catch because you were in a different session, they will be recorded so you can follow up on them. And then in the afternoon, we have a fireside chat with Paul Polman, former CEO of Unilever and the chair of the SBS board. We will bring together what some of these challenges mean for business. Without further ado, I really want to introduce Professor Myles. It's my absolute honor and pleasure that he's joining us this morning. He's a leading climate scientist who's most known for his groundbreaking work on attributing human influence to climate change and his role in shaping climate policy, including serving on the United Nations Intergovernmental Panel on Climate Change. And in fact, he's often known as the scientist behind Net Zero. Myles is the director of Oxford Net Zero, which is an interdisciplinary research initiative based here at Oxford, and professor of geosystem science at the University of Oxford School of Geography and the Environment, and head of the Atmospheric, Oceanic and Planetary Physics Department. And his research has really been instrumental in linking human activity to global climate change. But I think he will also have a message for you of how you can become leaders who contribute to the solution of climate change. And I think it's a very inspiring keynote lecture to kick off this bootcamp this morning with you. So I'm really grateful that you're joining us, and the floor is over to you, Myles. Thanks so much.
Well, thank you, and it's an honor to be here, actually, and seeing such a great class of 2025. A lot probably feels like it's changed over the past year on the climate issue, but some things haven't, and I brought with me a little visual aid to remind you of the things that haven't changed about climate and climate change. So each of these little lumps of coal, it's quite hard to find coal these days in the UK, each of these little lumps of coal represents 500 billion tons of fossil carbon. That's enough, if burnt and released into the atmosphere, to generate almost 2 trillion tons of carbon dioxide and, crucially, cause 1 degree of global warming. So when we first discovered this cumulative impact of carbon dioxide emissions on global climate, we, humanity, had just finished burning the first 500 billion tons. Started here in Oxford. I did my doctorate in the Hooke Institute. Robert Hooke did the basic science behind the steam engine. So Oxford's been at the heart of this for a while. Anyway, 250 years took us to burn the first 500 billion tons. That was enough for 1 degree. 16, 17 years later, we are 40% of the way through the second 500 billion. And that'll take us to 2 degrees. And there's plenty more down there, enough for 3 degrees, 4 degrees, 5 degrees. It all just depends on the ingenuity of our geologists finding this stuff. So, if I can convince you of anything, I want to convince you of this. I want you to remember this. We are going to generate more carbon dioxide by burning fossil fuels than we can afford to dump in our atmosphere if we're going to get even close to limiting global warming to well below 2 degrees, pursuing efforts to 1.5 degrees, in the words of the Paris Agreement. So the fundamental choice in climate, and this is cutting right to the punchline of my talk, just in case you fall asleep, is the choice we have between dumping that carbon dioxide in the atmosphere and disposing of it responsibly and permanently so it's not a problem for future generations. That's actually the fundamental choice in the climate issue between carbon dioxide fly tipping and responsible carbon dioxide disposal. The option of just not generating the carbon dioxide at all might have been an option back in 2009 when we first discovered, as I said, the cumulative impact of carbon dioxide on global climate, but it's too late now. We've generated too much. We will generate too much. We've probably generated too much already, and so we're going to have to get rid of it, getting rid of it at scale. And that's something I'm going to focus on quite a lot in this talk because it's not really appreciated, I think, by many people who are dealing with the climate issue. So that's a bit of overarching science to get started. But before we sort of get into the implications of that, I'm hoping I have some slides. I do. So I've given myself the title. There's various versions of the title around. Sorry about that. What the correct one is how we will stop global warming, because I am convinced we will stop global warming. Eventually, the question is when. And to start on a positive note, I want to convince you that we could stop global warming in 30 years. I've been saying that for 15 years or more. It's still true. We could have stopped, we could be halfway there by now, okay, but we're not, okay? So we could stop global warming in about 30 years, and crucially, that would limit the entirety of future warming to less than's happened since 2000. And that's quite encouraging. You should find that quite encouraging, okay? Because you'll hear a lot about, you know, we've missed 1.5 degrees or we're missing 1.5 degrees. I hear businesses coming to me saying, well, we can't do a 1.5 degree pathway now, so what does a 2 degree pathway look like? As if, like, oh, we can relax because we've missed 1.5 degrees, so now we may as well just think about 2. Okay? I'm sure you don't measure your portfolios in units of 25% of the number. You'd certainly lose a lot of money if you did. So we can limit future warming to less than that's occurred since 2000. But, and this is the crucial but, it requires fresh thinking in climate policy, the kind of thinking that I'm hoping this class will bring to the climate issue as you get out in your careers. Whatever you do, you will be affecting climate, both in your work and in your lives, but particularly in the companies you influence and the way in which you influence the world's financial system. The world's warming up. You've seen this a million times. That's what it looks like if you look at monthly temperatures. And notice they're quite often bumping over 1.5 degrees already. And we've understood why for a long time. A couple of weeks ago, somebody called me, I was one of those stupid people who was apparently got all our predictions wrong of climate, as in the words of Donald Trump from a couple of weeks ago. This is a figure from a paper published in the year 2000 on looking at the drivers of climate change over the 20th century. And you can see natural drivers contributed some fluctuations, but not the warming we see at the end of the series. Anthropogenic drivers capture that final warming, but don't capture some of this which happens in the middle. When we put them together, we get an almost uncanny reproduction of what was observed. The black line, of course, is what was observed. And now, 20 years on, we can add what's happened. Yes, Donald, we got it right. I wish we'd got it wrong, but we didn't. And that was in 2000. And we can go back a great deal further. In the 1970s, Bill Nordhaus published a paper in which he ran a model. He ran it on an ENIAC, I think, one of these computers the size of a room full of valves and things. But it was the first coupled climate economy model ever run, and he modeled what would happen if the world economy continued in the way it was evolving, using the science and the physics of how carbon dioxide affected climate. Came out of the work of Suki Minabe in the 1960s. And you can see there's a solid line there, which I'm sure he drew by hand. And then the calculation was the dashed line. And this was his prediction. And you'll see that at the time he made this prediction, global temperatures were declining. In fact, the newspapers, although not the scientific journals, that's another myth, the newspapers were full of predictions of the oncoming ice age. But they knew, the scientific community knew that carbon dioxide was going up, and they knew what carbon dioxide did, which enabled him to make this prediction. This is what's happened up until a few years ago. I haven't updated this slide, but as you can see, he got it right. He predicted we would reach 1 degree in the past decade, and we did. He also predicted we would see a significant acceleration in warming around now, reaching 2 degrees around 2040. We've got to hope that that part of the prediction was wrong, because, of course, this was a prediction without any measures to do anything about climate change. This was just Bill Nordhaus imagining what would happen if the world economy just carried on evolving the way it was from the 1970s onwards. And we have, of course, made a lot of progress, certainly in talking about what to do about climate change. And the Paris Agreement has, I think we can give it credit for, stabilized emissions. It's not started emissions going down yet, but emissions are no longer rising. So that acceleration that Bill Nordhaus was predicting, that was expected to occur as a result of the ever-increasing rise in emissions, we have to hope is not going to happen. So this is real. This shows you temperatures and the different drivers brought up to date from the influence of natural drivers in blue, influence of other pollution, aerosols mainly, which, as you can see, was cooling the planet, but is now, thankfully, going away. That's because large parts of the world suffered severely from local air pollution, which while it did keep the planet cool, it also killed millions a year from smogs and respiratory illness. So it's good that that's being cleaned up, but it does mean we're revealing more of the underlying warming that's caused by the greenhouse gases. So you can see we've reached 1.3 degrees or so, and warming at the moment by between 1/4 and 1/3 of a degree per decade. At that rate, we'll reach 2 degrees around 2050, okay, 10 years after Bill Nordhaus predicted we might, and over 3 degrees by 2100 if we just continue warming at the current rate. And remember, this stuff, the carbon dioxide emissions on global climate are cumulative, so as long as emissions continue, the warming continues to rise. Every ton of carbon dioxide we dump in the atmosphere drives up global temperatures by another 1/2 trillionth, if you're into interesting numbers, of a degree. But we're dumping it in. That 1/2 trillionth of a degree doesn't sound like very much, but we are dumping it in at a rate of 40 billion tons per year. So the argument, and interestingly, I mean, one thing about this sort of climate skepticism 2.0 that we seem to be going through at the moment is that it doesn't seem to be about whether it's happening. You know, a few heads of state aside, most people tend to accept that carbon dioxide emissions are warming the planet, and the carbon dioxide is arising from human activity. If you want to talk to me afterwards about your theory about how it's all volcanoes, feel free, but I hear that conversation a lot. And I'm always happy to talk it through, but we aren't seeing, fortunately, a big change in the view on what's driving climate change. What we are hearing is lots of comments on how, well, it's not that bad, you know. And so when the 1.5 degrees report came out, we had headlines in The Guardian, we've got 12 limits to limit climate catastrophe, was the Guardian's head, 12 years to limit climate catastrophe. And this was in 2018. And this really triggered a lot of, 12-year deadline rhetoric, and now we're sort of in 2025, 5 years off from 2030. What did all this, what we might call deadlineism, achieve? And by the way, at the time, we actually, as authors of that report, I was one of them, we actually worked quite hard to try and explain to people we weren't setting a 2030 deadline. That was not what the report said, but it was what the journalists wanted to read in it. And the difficulty with this is that then you get the sort of counterblast from the other side saying, wait a minute, 12 years left, let's talk about this. And this is a tweet from Bjorn Lomborg showing various estimates of the impact of climate change on the world economy, saying, hang on a minute, it's sort of a few tenths of a degree, a few percentage points of GDP in 2100, or as he would put it, that's a couple of years of growth, is all that climate change actually does to the world economy. Now, what I want to ask is how much on the sort of question of how much climate change matters do people actually disagree? And this may surprise you because it seems like an issue where people disagree very fundamentally on the importance of climate change, so to speak. But let me show you some evidence that actually the disagreements may be not quite what they seem. We can argue about the numbers, about how much damage we expect climate change to cause at different levels of warming, or equivalently, or how much to value that damage, how to add it up. These are deeply contestable questions. But everybody pretty much agrees on the shape. As you can see, I've just put this line over Lomborg's, and you can see it's got that curved shape. As you move away from a pre-industrial climate, we expect to see the rate at which damages accumulate increase per degree of warming. So we see not only damage accumulating, but damage accumulating faster as you move away from that pre-industrial climate. And the reason for that, I quite often like asking the class about this one, but it's a big class, so I won't, if you forgive me. The reason we're pretty confident about that is because we know that a lot of the systems of our planet, including our own agricultural systems and our economies, have evolved, have been built on that pre-industrial climate. So if we were to move away from it in either direction, it would cost us. And that means, you know, as a physicist, I'd love to use the phrase to first order, but that means, you know, to first order, to a first approximation, that's the shape of the curve. Nothing else is really possible when you're close to your pre-industrial climate. As we get further away, of course, bad stuff could happen. The curve could go non-linear. But at the moment, that's exactly the kind of progression we expect to see. And if that shape is the quadratic shape for the damage curve, has some very simple implications. If we take Lomborg's word for it, and 3 degrees of warming is 2 to 4% of GDP, then 1.5 degrees of warming would be a quarter of that, because 1.5 is a half of 3, and so 1.5 squared is a quarter of 3 squared, okay? It's the most complicated bit of mathematics in this entire lecture, don't worry about it, but I'm sure you can cope with it. 6 degrees of warming would cause 8 to 16% of GDP. And remember what I said about the shape, about going towards global cooling as well. I reckon 6 degrees of cooling, which would look like this, might cost more than 8 to 16% of global consumption. But, you know, you can form a view. We've actually moved on a long way from the studies that Bill Nordhaus was quoting in that paper, in that we're now using estimates of observations of economic activity, relating them to meteorological variables to make data-driven predictions of the impacts of climate change over the coming century. And this is an early example of this work from Felix Pretis, a graduate of Oxford, I think possibly a graduate of the MBA. He did various degrees here, including a doctorate in economics. And he showed if we limit warming to 1.5 degrees, how we should expect damage to accumulate in future, even, you know, despite the fact that we've stopped the warming, we still see the harm from climate change continuing to accumulate, but reaching around, this is 1.5 degrees in 2100, reaching, you know, a loss of some 8% of GDP as the best estimate in 2100. If we go to 2 degrees, it's over 10%. And you see in the colors here, the purple colors are the countries whose GDP growth per year is adversely affected by, significantly adversely affected by a warming of 2 degrees. And you can see by significantly here, it means even the data to date of climate fluctuations and their relationship with global temperature is enough to say these countries will be adversely affected by further warming. And so the other ones, if you're in one of the grey ones, or perhaps in a green one, if you come from a green one, where the evidence suggests a modest benefit from a small amount of warming, you can see the overall pattern here, but you can also see, crucially, the inequality of climate impacts around the world, the fact that the vast majority of countries that are adversely affected by climate change are the ones whose GDP is relatively low, GDP per capita is relatively low in the first place, and also the ones that are overwhelmingly not responsible for the warming to date, for the accumulation of carbon dioxide in the atmosphere to date. You had a question on this one.
Can you help us contextualize when you talk about the GDP loss? I know that there's so much within that. It conveys as a metric, but I'm curious if you can give us the storyline about the effect on like food supply, the effect on jobs. Like, what does that actually?
That's okay. If I could dodge that one, that's a whole lecture, and I commend you. Ben Franter, for example, who some of you will be hearing from shortly, works on precisely this, sort of identifying actual harms from climate change. but there are people in the room who know that I can give that lecture, but it's just not the lecture I was going to give. But yes, that's how these harms are manifest through impact on food supply and through impact, crucially, on a globalized economy, which is why this kind of research, it's backward-looking research. It looks at how climate has affected the economies of different countries around the world over the past 40 years to say something about the future. And that's why we should be careful about, like any advert for a stock picking program, the past is never a perfect guide for the future. We need to be careful, for example, if we're in a country that appears to be not in the front line of climate change impacts, we also live in a fully globalized economy, and we are therefore going to sort of experience the impacts indirectly of other countries. And within this paper, Felix sort of separated out, and we just zoom in here, just for your interest, because I know it's a very multinational crowd here. It's always worth zooming in to find out who's in line who's in the firing line, so to speak, from climate change. Interesting, you'll see Saudi Arabia right near the bottom there. You might expect to see Bangladesh and Djibouti, but Saudi Arabia, what's that doing there? Well, this is a measure of the direct impact of the warming on economies. And of course, Saudi Arabia is an extremely exposed economy to warming because it's a very hot place in the first place. It's not, of course, accounting for the impact of the drivers of the warming on the economy, so which, of course, as you all know, has a major impact on Saudi Arabia as well. So, what we can't say as scientists about the cost of climate change is, putting numbers on things that are inherently subjective. So, what is the statistical value of life? Are poor lives worth less? How can you even ask that question? But if you actually look at, indeed, empirical studies of the impact of climate change on GDP, if you really drill into the assumptions that underlie those studies, you will find an implicit assumption that poor lives are worth less because they're not earning as much. If a poor person dies, their impact on global GDP is less than that of a rich person. Now, I'm not saying this is, I'm just emphasizing this sort of shocking way of thinking to shock you, to make you think, okay, well, you shouldn't be thinking that way, but that makes it inherently challenging to add up the impacts of climate change. If you just look at, impacts on GDP, you will, without thinking about it, inherently, accidentally value poor lives less than rich ones. And the social impacts of climate change to think about as well. If we have mass migration from poor countries to rich countries, that actually increases global GDP. Yeah, I'll leave you to think about why, okay? But it has other consequences as well, which we're seeing in the politics of Britain and Europe right now. Then there's the big question about time. Climate change primarily affects the future. Dealing with climate change is something we need to do now. So the relative impact of damage on future generations relative to costs on this generation is obviously fundamental to this. And also the value we assign to risks, planetary scale risks, low probability events like tipping points, the collapse of the Greenland ice sheets, sudden rapid sea level rise, and so on. How do we value those things when we don't know when and if they're going to happen? And yet, if they did happen, would have very, very profound consequences. But what we can say is both the risks and the impacts of climate change go up faster the further you go away from pre-industrial climate. So whatever it is, so I don't know what the number is, call it D, okay? 1 degree of warming, what we experienced in the 2010s, caused, a certain amount of damage. You know what it was because you felt it. Or just, think about the past decade. That's the amount of damage we're experiencing at 1 degree of warming. 2 degrees will cause 4 times as much, at least, because that curve is getting ever steeper. 1.5 degrees would cause 2.25 times as much. Again, I'm just doing the numbers in my head. And that means 1.25 degrees, which is roughly where we are now, or where we were a year or so ago, would be 1.6 D. So just doing some maths here, you'll realize the difference between 1.5 degrees and 2 degrees does the same amount of damage, is expected to do the same amount of damage as all the climate warming we've experienced to date. So I don't know what the number is for the total value of that damage, but it's at least the same again as to what we've already experienced, and that's just the difference between 1.5 and 2 degrees. And that's the case, fundamentally, why we do need to stick to our guns, to stick to the Paris Agreement target, to limit warming well below 2 degrees, and pursue efforts to limit it to 1.5. And what that means is very simple. Again, you don't need a complicated scenario or a climate model to work out the implications of that. Yes?
This might just be re-asking the earlier question in a different way, but hopefully not. So with the dam and construction, what all is that including? Is that also including like the increase in natural disasters and damage from that? Or like, I guess what all is that?
As I stressed, in principle, yes, because I don't say what the value of D is. I'm just saying what the shape of the curve is. And that's what I'm trying to stress to you. We can agree on the shape of the curve. We can argue till the cows come home about exactly how big the curve is. But that doesn't change the fact that the difference between 1.5 and 2 degrees is at least as bad as what we've already experienced. So when you're out talking to people about it, saying, well, these days it's kind of easy to talk about climate change because everybody's experienced it. We're all feeling it. Okay? And we're feeling the impacts, we're seeing the impacts economically, and we can say with confidence that that difference, ceding 2 degrees, if you like, is going to cost, and is going to cost at least as much as we've already experienced to date. So that's just to put it in context and why I would argue that nothing has changed in the fundamental case to actually go for the goal of the Paris Agreement, which is to limit warming to well below 2 degrees, pursuing efforts to 1.5. And this is where the rest of this lecture will be about how, but I'll just, this first part should motivate the sort of how fast question, because again, you don't need a climate model to know that if we're warming at 1/4 to 1/3 of a degree per decade at the moment, if we want to stop the warming at a particular level, we're going to have to hit the brakes. And if you can remember your driving theory test, if you're driving along and it's a second before you reach the junction, if you hit the brakes immediately, you've got 2 seconds to stop. Yeah? The 2 comes from the fact that you're slowing down. Okay? You probably remember drawing curves, integrating under the speed curve, anyway, all that sort of thing. So, exactly the same logic. If it's 5 years before we reach 1.5 degrees, we've got 10 years to stop if we want to limit warming to 1.5 degrees. So that's kind of where we're at the moment in terms of the underlying rate of warming. Could we stop climate change in 10 years? We probably could, actually, technically. Will we? I doubt it. Certainly they're not planning to. But conversely, if it's 25 years before we reach 2 degrees, if we want to limit well below 2 degrees, we need to stop the warming well below 50 years. So we've got much less than 50 years to stop the warming. And aiming to stop the warming in 25 to 30 years' time is, as I said at the beginning, entirely feasible, but it means a clear understanding of what we need to do and some fresh thinking in how we set about it. What does it take to stop the warming? Well, this was the phrasing in that 1.5 degrees report that summed it up. Some jargon in there, so anthropogenic means human-induced, and when we say declining net non-CO2 radiative forcing, which is a bit of a mouthful, what we mean is other emissions, mostly methane. Okay, so we need to get to net zero global human-induced carbon dioxide emissions, and we need to get methane emissions on a decline. They're currently rising rapidly, causing a lot of warming. And that would be enough to halt, carefully chosen word that one, human-induced warming on multi-decade timescales. We weren't able to predict that it would stop the warming forever, because of course forever is a long time, and the long-term adjustment of the system is still much unclear, but it would be enough to stabilize temperatures for a matter of decades. So what does this mean? So here you are, this is what it takes. Carbon dioxide emissions. So I mentioned methane there, and again, those of you who've heard my lectures know there's a whole lecture on methane. Methane is very important. It's very important we get methane emissions under control, and they're currently out of control. And so that's an important part of it, but it's not the one I'm going to focus on, because carbon dioxide ultimately is the driver of climate that is accumulating in the system, that is our principal legacy that we pass on to future generations. So if you'll forgive me, I will focus on carbon dioxide, on the carbon dioxide challenge for the rest of this talk. And what it takes to stop global warming in terms of carbon dioxide here is we have to reduce the net emissions from energy and active, and I've bold-faced active there, deforestation to zero. And that results in at the moment, about half of the carbon dioxide we dump in the atmosphere stays there every year. The other half is taken up by the oceans and the land biosphere. And this is where this talk is going to start getting a little bit techie, but I'm ready to bet that all of you are going to leave this course this year and get into carbon trading in some form. And so it's really important that you understand what I'm about to tell you about the way we're setting up carbon trading. So, about half of the carbon dioxide we dump in the atmosphere every year stays there. The rest is taken up naturally, well, semi-naturally as it were, by the oceans and the land biosphere. When I say semi-naturally, they wouldn't be taking up that carbon if it weren't for the fact that we'd pumped out an awful lot historically. Yeah? I mean, back in the 18th century or 17th century, natural carbon fluxes into and out of the oceans and the land biosphere were in balance. But of course, we pushed the system so far out of balance, there's a steady flow of carbon dioxide into the land biosphere, trees, plants, soils, and the oceans right now. And it's 20 billion tons a year. So it's very important that this is happening. If it wasn't happening, we'd be in even bigger trouble than we are now. And we expect that phenomenon to continue. After the date of net zero, that so-called passive uptake, that response of the land biosphere and the oceans to just more carbon dioxide in the system, continues for centuries, drawing down atmospheric concentrations of carbon dioxide and stabilizing global temperatures. So, crucially, stabilizing atmospheric concentrations of carbon dioxide, which was the goal of climate policy for many years, up until the Paris Agreement, isn't enough to stop global warming. You actually have to have carbon dioxide emissions, carbon dioxide concentrations in the atmosphere, the level of carbon dioxide in the atmosphere coming down, and you achieve that by reducing emissions, that's the sum total of emissions from fossil fuels in industry and active deforestation, to net zero. This was established back in 2009 and was really marked a big change in the focus of climate policy. From focusing on stabilization, we shifted in a remarkably short space of time. The Paris Agreement was only 6 years later, to acknowledging the need for net zero emissions. And the way the Paris Agreement acknowledged that was in Article 4, in order to achieve the long-term temperature goal of Article 2, which is limiting warming to well below 2 degrees and pursuing efforts to 1.5, the parties agreed to achieve a balance between anthropogenic emissions by sources and removals by sinks of greenhouse gases in the second half of this century. That was what the Paris Agreement agreed they were going to aim to do. Yes?
How certain are we that post net zero CO2 emissions that the passive uptake will keep going on? And it's
For low levels of warming, i.e. sort of 1.5 to maybe 2.5 degrees, we're pretty confident. We understand the carbon cycle and the ocean response pretty well. It's a very good point. The higher the level of warming, the less confident we are that we won't somehow irreparably damage the oceans or the land biosphere such that they just can't do this service, provide this service for us anymore. And that's actually one of the big risks at higher levels of warming, is that the biosphere in particular just collapses. But at low levels of warming, it's a prediction, sure. We've never tried reducing emissions at that rate. It's one which we hope we will test over the next few decades. But it's one where at the moment, all the modeling evidence is, it is modeling evidence, because as I say, we've not observed this, but these are models calibrated with the observation things we can observe, and we believe that will occur. And as a result of that Paris balance commitment, many countries since Paris have made net zero commitments. One notably has stepped away from its net zero commitment. You can see what's going on in the net zero tracker, which is maintained here in Oxford. And I just want to draw your attention to a few countries that are blue in this map. These are countries that have achieved net zero already. And with apologies to any Guyanese present, I was going to focus in on Guyana as an example, because it's a really interesting one to challenge our thinking on what we mean by net zero. Is anybody from Guyana on this course? I mean, it's a tremendously impressive country doing a huge amount on climate, but it happens to illustrate some of the challenges we have in understanding what net zero needs to mean to deliver what we said it would deliver in 2009 to halt global warming. Because Guyana, in case you didn't know, is also a very substantial producer of oil and gas. They've recently discovered very significant oil and gas reserves, which they are, as they are fully entitled to do, providing to the world. So what's going on here? How can Guyana claim to be a net zero country already while being a major producer of oil and gas with the associated emissions in the oil and gas industry? Well, the answer is the way we've defined balance, or specifically what people mean by balance and net carbon dioxide emissions in the context of the Paris Agreement. So people like me, IPCC authors, carbon cycle scientists and so on, mean emissions minus what you remove as a result of active, ongoing human intervention. For the UNFCCC, the United Nations Framework Convention on Climate Change, and just about everybody else, including all the companies you're going to go and join next year, it also includes carbon uptake on what's called managed land that is happening indirectly as a consequence of past emissions. And suddenly lots of land is managed. So Guyana has declared large parts of their forest managed land because they're protecting it. They're doing a very good job protecting it. It's a very good thing that they're protecting that forest. But that allows them, under the rules, I'm not suggesting for a second that Guyana is not doing exactly what it's entitled to do by the UNFCCC accounting rules, that entitles them to claim all of that carbon that's being absorbed by Guyana's forests as a result of historical emissions, as if they were actively taking it back out of the atmosphere. This is happening. We are seeing these are photographs of the same place in an African savanna. You can see from the background, it's the same photograph from 1925, 2011, to 1993 and 2011. You can see how the vegetation has been transformed. And Midgley and Bond have studied this and shown that that's happening, not because of any change in local land use practice. They chose this because it was an area where the land use had been left alone unchanged for the past 100 years, but because there was just more carbon dioxide in the atmosphere. So it's a good thing it's happening. And it's a very, very good thing that countries like Guyana are protecting their forests to allow this to happen. But if we take advantage of this as if it was a negative emission, fully compensating for the impact of our ongoing fossil fuel use, we see interesting things like this. Canada's forests sink, even with the occasional forest fire, over the 20 years, 2001 to 2019, was almost 1 billion tons of carbon dioxide per year, just because Canada's forests were growing faster because of all that extra CO2 in the atmosphere. Canada's emissions were about 750 million tons. I'm not suggesting for a minute that the present government of Canada has any intention of saying, hey, we're net zero, so let's not worry about it. But if things had gone another way earlier this year, we might well be seeing a government of Canada that was saying we don't need to worry about net zero anymore because Canada can claim, by just declaring all Canada's forests managed, Canada can claim to be net zero already. So I'm emphasizing this because it's got a problem. You know, we have a problem here. It hasn't started yet, but it could. If you want to make money, start selling carbon offsets based on managed oceans. Remember, 30% of the world's oceans are in somebody's economic exclusion zone. A couple of you are smiling at this point. No, I didn't mean that. Please do not. No, because if we classify all of this natural uptake of carbon dioxide by the land and oceans as removals, then we would need to drop emissions well below zero in order to stop the warming, because we then would have to be, as it were, pretending we were actively drawing down those carbon dioxide concentrations in the atmosphere. You can see here that this is the same graph, but just taking the gray above the line is the same as the green below the line. So we've just renamed all that green as if it was a negative emissions, making our net emissions much lower. Hooray, it seems to be a great result. On the other hand, what it means is we then have to go well below zero in order to stop global warming, because adding up all of these emissions, we need to be drawing atmospheric concentrations of carbon dioxide down if we're going to stabilize global temperature. And if we reclassify passive uptake as a negative emission and then just aim for net zero, which is probably what most people think they're going for, all we will do is stabilize concentrations of carbon dioxide in the atmosphere, bring the net flow of carbon dioxide into the air to zero, and that is not enough to stop the warming. You can see the temperatures carry on rising. Even more extreme, you could say I'm getting a bit carried away here, but hey, it's not far off what's happening. Stabilizing concentrations allows more warming. If we fully exploit Article 6 to maximize the amount by which we rely on passive uptake through the international offset markets, we could actually defer, we could pretend we were on a path to net zero in 2050, but actually defer reducing any active emissions at all for 15 years and end up with even more warming, end up well north of 2 degrees by 2100, even though we're nominally on a path to net zero by 2050. Yes?
So when you talk about stabilizing atmospheric carbon concentrations and warming would continue to rise, is that to some asymptote or is that just continuous?
After a few centuries, it would restabilize. I'm talking about thanks, that's a good question, but just to simplify, it's easiest to think of stable concentrations gives you ongoing warming, roughly 0.3% per year, yes, eventually, it would asymptote, but exactly where it would asymptote to is, because it's a multi-century prediction, is really hard to predict.
I know when carbon is taken out of the atmosphere, after a while it gets re-released. So based on for Guyana, for instance, the protecting line, what's the permanent?
No. Again, to be fair on Guyana, their forests are growing, and if they keep looking after them, that carbon will stay there. You could sort of make it's safer to make jokes about Canada because there's probably plenty of Canadians in the room. You could argue that if Canada works the same trick with all the forest fire activity that's happening in Canada, it's a lot less safe. But you're right. There is something fundamentally unsafe, so to speak, about carbon stored at the Earth's surface, because as the climate changes, the viability of those forests may change. Let's hope we don't change the climate enough to affect the viability of Amazonia, for example, but that is one of the risks. People are looking at that. And of course, if the forest dies because of global climate change, then you could say, well, it's not the fault of Guyana, that was just climate change, but the net result is the carbon still ended up in the atmosphere. And so that's the difficulty with this sort of, this pretense, if you like, that we can compensate for ongoing fossil fuel use by just planting trees or protecting trees. Important though it is to protect trees anyway. So the point is, we need a like-for-like balance, if you can remember that phrase, between geological sources, things like burning fossil fuels, and geological timescale sinks. That is, disposing of carbon dioxide permanently on multi-century to millennial timescales. We'll talk a bit more about what geological timescale sinks needs to mean in a minute. Yeah.
You might be going this direction, but which definition of balance does the carbon credit market use?
It uses the UNFCCC one. Okay, there would be people, and maybe talk to Jimmy about this, there are people trying to fix this. But at the moment, the new UNFCCC one is, I think it's fair to say it's kind of in reach. So not everybody uses it, but you can probably get away with it. Yeah? So even though there will be people who tell you firmly, no, we don't use that definition, it's like, yeah, but you could. And when a market is sort of efficient, people tend to gravitate towards the easiest option. And it's obviously a much easier definition of net zero than... And certain markets definitely use it. And of course, Guyana will argue they are actually making steps to actively regrow their forests as well as protecting the forests they have. And so it's, as ever, it's always a little bit complicated because, I'm not suggesting that the markets are, fraudulent in any way. I'm just pointing out this big black hole, as it were, in carbon accounting. People like... We need to do two things. We need to achieve this like-for-like balance. If we're pulling it out of the geosphere, pulling it out from the ground, we need to be putting it back or getting rid of it permanently in that way. And we need to protect these passive carbon sinks. These are ands, not or. And the problem that they have at the moment is by focusing on just the flow of carbon into the atmosphere, we're kind of muddling these things up. And if you're interested, this is the state of Geological Net Zero that we talked about in a paper just appeared earlier this year, which was making the point that we need geological net zero, we need this balance at the Earth's crust. If you're taking carbon out of the Earth's crust, you need to be putting it back or disposing of it somewhere equally permanent. And we need to separate out the accounting for land sinks so that we can ensure that we are taking steps to protect these vital natural sinks to ensure they continue to provide this carbon disposal service we need into the future. So that's the sort of, that's the science part of this talk. And I'm now going to sort of crack on with what I think the implications are for policy. And I'm going to start with a quote, and which is, I would argue, is a quote that illustrates why, this quote and the reaction to it, illustrates why we need a fresh approach to climate policy. And it's a challenging quote, intentionally so, and comes from the president of COP28, Sultan Al-Jaber, who's also he was seconded to the COP from his role as Chief Executive Officer of the Abu Dhabi National Oil Corporation. This COP28, which happened in Dubai a couple of years ago. And shortly before the COP, Sultan Al-Jaber was in an interview and a discussion online, and he said this: there's no science out there, and then I think he corrected himself, said, oh, no scenario out there that says that the phase out of fossil fuel is what's going to achieve 1.5 degrees. And I think it's fair to say, when The Guardian sort of did an expose of this on day one of the COP, the world went a bit nuts. And all piled on, saying what a terrible thing for him to say, he's denying the science, this just goes to show we shouldn't have held the COP in a petrostate and, you know, et cetera, et cetera, et cetera. What's interesting about that statement, apart from the fact that it caused this, and those who've heard this lecture before perhaps backtrack on this, comment on what he's said.
That just simply the phase out is not going to actually get us to 1.5?
Yeah. So it's true. The Guardian, in a subsequent article, said they could only find one scientist in the world who was willing to acknowledge this statement was true. No prizes for guessing who that scientist was. The reaction from everybody was, no, we've got to phase out fossil fuels. This is how we're going to achieve our climate goals. It's not. We might have achieved our climate goals if we'd started trying to phase out fossil fuels in 2009 when the climate goal was 2 degrees. Remember, that was Copenhagen. But we didn't. And we show no interest in phasing out fossil fuels to this day. So that's not how we're going to solve this problem. And it's not how we solve this problem even in the most optimistic scenarios that meet the goals of the Paris Climate Agreement. These are the scenarios of the Intergovernmental Panel on Climate Change in the most recent report, showing you global primary energy generated from oil. And you'll notice it comes down, the thick lines are some scenarios from the International Energy Agency, but don't worry about them. But you can see the gray lines show a substantial reduction in the amount of energy we generate from oil between now and 2050 or so, and then it stabilizes at maybe 2/3 or a third to a half of the level it's at the moment. Gas is even more confused. Some scenarios go down, others actually show an increase in energy generated from gas over the course of this century. The one clear message that does come out of these scenarios is coal. We do stop using coal. And if we don't stop using coal, we won't stop global warming. I think that's a pretty unambiguous message, mostly because coal no longer makes economic sense anyway, and the countries that are having to invest in it are doing so because of economic drivers beyond their control. If I add these things up, the red lines here show you the carbon dioxide that's generated from fossil sources in 1.5 degree scenarios. And as you can see, we do burn less. We replace fossil fuels with wind and solar, and thereby avoid generating some 2 to 3 trillion tons of carbon dioxide by 2100. Okay? That's another of these mind-bogglingly big numbers. Don't worry about the number itself. Just remember 2 to 3 as a unit. Okay? That's what we avoid generating by replacing fossil fuels with wind and solar in these scenarios, in the scenarios that meet the goals of the Paris Agreement. So the red lines, none of them go to zero. Some of them get a little bit close in 2100. So you're probably thinking, well, what's going on here? I mean, I was telling you we need geological net zero to stop global warming. I was telling you we can't do it with the biosphere. So what's happening? How is it that these scenarios still, that these are the scenarios that actually limit warming to 1.5 degrees, which means stopping the warming shortly after mid-century? Well, I'm showing you here the carbon dioxide that's generated by burning fossil fuels. That's not the same as the carbon dioxide released into the atmosphere. This is the carbon that is captured and stored geologically in these scenarios back underground, captured with plants like the schematic here, although there's plenty of real ones out there, where the carbon dioxide is captured, where it's generated, purified, compressed until it's a liquid, at which point it has much the same density as the hydrocarbons it probably came from, and re-injected back into sandstone rocks underground, exactly the kind of rocks where the hydrocarbons were to start with. In fact, quite often, when they drill to look for hydrocarbons, they find liquid carbon dioxide, because it looks just like a hydrocarbon in the seismic data. So then, of course, they're very disappointed, because it wasn't what they were looking for. But the point is, we know that carbon dioxide, there's a lot of carbon dioxide in the Earth's crust naturally, and we know it's therefore possible to put carbon dioxide back. And we also know it's possible because the industry's been doing it for decades, at a pretty small level, around 40 million tons per year, and the vast bulk of the CO2 that we inject stays there, and if you choose the location right, you can make sure that it all stays there. So in these scenarios, we dispose responsibly of roughly 1 trillion tons of carbon dioxide restored to the geosphere, put back underground by 2100. So 2 to 3 avoided, 1 disposed of, okay?
Are there any kind of like earthquake risks that come with that? Because I know that some
We're going to come to this, but let me take that straight away. If you do it badly, like if you inject too fast, after all, what you're doing here, you're injecting fluid under pressure into rocks, which is also known as hydraulic fracking in a different context. It can trigger seismicity. But there is a crucial difference. When you're injecting to get stuff out, you want to break the rock. You want to fracture it. That's the point. When you're injecting to get rid of the CO2, the last thing you want to do is break the rock. You want to keep it intact because you want the CO2 to stay there. So you inject under a very different pressure regime. It's a different process to fracking, even though it involves much of the same technology. The objective is different. And if done well, you can store the carbon dioxide there indefinitely. And they've been, as I say, there's projects which have been doing this for decades, and they can monitor the underground plumes of carbon dioxide, see where they diffuse to, and see what happens. And we know this works. Not only do we know it works, we also know we're utterly counting on it to meet our climate goals. And the big danger is, how many people in this room knew that we were planning in our 1.5 degree scenarios to get rid of 1 ton of carbon dioxide back underground for every 2 to 3 we save by replacing fossil fuels with wind and energy? That level, this part of this, I know the people who've heard this lecture before should better put their hands up at this point. But the point is, how many of you knew that it was that big in our climate future? It's a minority, okay? Most people don't like to talk about this stuff because it's kind of seen as a nasty end-of-pipe solution. We'd much rather talk about solar and wind. We'd much rather talk about avoiding deforestation. Everybody loves trees, of course. And in these scenarios, we do save about 0.4 trillion tons of carbon dioxide by reversing deforestation, by stopping deforestation and starting to reverse it. But again, look at the numbers. 2 to 3 avoided, 1 back underground, less than half a trillion through reversing deforestation. Without that geological storage, we're not going to meet our climate goals. Yes?
You might be getting to this a bit further in the lecture, but can you kind of talk to us a little about how the economics of
Yes, and I will. Yeah. I hope.
Currently,
okay.
$900 a ton.
Okay, no it isn't, and you're thinking about air capture, and we'll, okay, and, yep.
Next to air capture and geological storage, can you talk to all of those technologies considered in the scenarios already existing, tested at scale?
Tested at scale is the difficult one, of course, because what do you mean by scale? I mean, as I say, we inject 40 million tons of carbon dioxide per year. We need to be up at the billions. So no, we haven't deployed carbon dioxide, geological carbon dioxide storage at scale, at the kind of scale we need to deploy it, but that's just what happens. I do wonder, before the London sewers were introduced, did anybody ask, have sewers ever been tested at scale? Okay, and the answer would have been, well, no, but it's still a good idea. So I think that's, but The Guardian routinely, I think they have an editorial policy that whenever they mention carbon capture and storage, they put in brackets an untested technology, okay, which is simply a lie. Okay, sometimes they say untested at scale, which makes it not quite a lie, but still very misleading. Okay? As you can tell, I'm not a fan of The Guardian's coverage of carbon capture and storage. And of course, coming back to somebody's question around here earlier on, if we store carbon at the Earth's surface, it's vulnerable as the climate continues to change to end up back in the atmosphere. So if we just look at the sort of scale of the challenge, if we want to, the contributions to avoided warming by 2100 in Paris compliant scenarios, 65% of it is from avoiding producing carbon dioxide in the first place, 25% of it from getting rid of carbon dioxide back underground, and roughly 10% from reversing deforestation. And because it's not happening, we're not on these scenarios at the moment, we're not reducing the rate at which we generate carbon dioxide from burning fossil fuels, some of that slack will have to be taken up by more geological storage. Because the biosphere, we've only got the one biosphere. We can't say, oh, well, don't worry, we'll just plant more trees. We're already counting on the biosphere to do a lot of the work for us, and we're counting on it doing even more in the future because of the need for the biosphere to mop up the carbon dioxide that we've generated historically. Yes?
Sometimes you hear the narrative around the beef industry and how that could reduce carbon, but is that significant at all?
It's very significant, and it's another lecture. I'm sorry. I'm going to start using that response. And a very interesting lecture, I can assure you, but if you don't mind. Because I sort of said we'd worry about methane. I kind of, yeah, but it's part of the methane story. Yes?
If we're talking about reversing deforestation, is that strictly defined as the direct ongoing human activities? And isn't that a bit tricky to distinguish?
Yes, it is, absolutely, which is why we've got that huge hole in accounting and why you need to all worry about that part of this lecture when you go out and learn about carbon accounting from Jimmy Gia and then subsequently go on to probably work in the carbon industry in the future. Go back to that part of this lecture and really think about it, maybe even read the paper behind it, because it's such an important issue about that fuzzy dividing line between what's actually a consequence of ongoing human activity and what's happening because of historical emissions. It's a dividing line that I would argue we just can't make, and therefore we need geological net zero, which means we need a like-for-like balance between what's coming out of the Earth's crust to what's going back in. One thing's for sure, nothing comes out of the Earth's crust by accident. I mean, you know, there's a small flux from volcanic activity, but, you know, we know what comes out of the Earth's crust. You know, we know where this came from. And we absolutely know what's going back in, not very much at the moment. But again, it's very easy to measure. Have you disposed of carbon dioxide permanently? If you've injected it back underground, you can measure that. If you're talking about storing it at the Earth's surface, it's harder to measure. Yep. Far away.
If we can capture and store CO2, is it at all possible to use it as a fuel?
You could, but okay, it's a really interesting question. I would argue that it doesn't make sense to do so because you have to add so much energy to turn the carbon dioxide into something useful. You're actually much better off just sticking it underground, which takes relatively little energy, and burning a fossil fuel. Yeah? So, yes, there's a lot of enthusiasm about so-called e-fuels, so basically fuels made from carbon dioxide captured from the air and with renewable, you know, and using renewable hydrogen to turn them into fuels. But I think as long as energy is not free, until you get to the point where renewable energy is free, I just don't think they make any sense because of the energy penalty of turning carbon dioxide into. The problem with carbon dioxide is it's so stable. I mean, this is why it hangs around for hundreds of thousands of years. It's a really, really boring gas. Yeah? You can't do anything with it. And that's why we've just got to accept the fact we've just got to get rid of it at scale. I mean, it doesn't mean there aren't some uses, interesting uses and so on, but again, at the scale we need, there doesn't seem to be much option apart from just permanent disposal. Yeah. Sorry. Sorry. Somebody over here has had a question for a while. Oh, sorry, yeah.
I think the question I had was around population. Population is growing at a very crazy rate, and even if we think about reversing deforestation or think about these ways, we keep coming back to the conversation on as people grow, they're going to need somewhere to live, they're going to keep producing significant amount of waste. How do we get to think about that as we address this conversation? And what is the place of vulnerable people?
Yeah. No. I think it's a great question. I mean, I'm old enough to remember when the sort of 1970s population boom projections were being made. And in many ways, the great good news story of the past 50 years has been that those predictions didn't come true. Okay? Global population is still rising. It's rising at a frightening rate in certain parts of the world, and that's, a cause for considerable concerns. I'm not at all pushing this back to you saying that don't worry about population. Of course, there are demographic trends that we need to be concerned about. But I guess the best I can say is, well, it could have been a lot worse. And actually, I think it's one of the great good news stories of the past 50 years. And what I love about this story is that overwhelmingly, it's as a result of decisions made by literally billions of women in developing countries, and not particularly by men in suits making policies. And I think that's actually a real sort of something to remember about things that humanity has got right over the past 50 years. We got plenty wrong. Those men in suits have been good at that. But we are getting some things right. It's an MBA course. You're going to be thinking about investment. And I pointed out to you that geological disposal is 25%, at least 25% of the solution, and it's getting less than 1% of the investment in the transition. So from Bloomberg New Energy Finance here, if I highlight all the investment that's relevant to avoiding producing carbon dioxide, like things like power grids, investing in electrification of transport, so electric cars, renewable energy, the big blue bar at the bottom, these are the big ones. These are all about avoiding using fossil fuels. There's two little ones in the middle there, hydrogen and carbon capture and storage, that you might say are remotely relevant to scaling up the amount of carbon dioxide we dispose of. So this is the problem, which is why I focus on this, is that, why is this? Why are we not investing in something when we know it's such a huge part of the solution? We need people to recognize the need for geological net zero. So that's this like-for-like balance between carbon dioxide we still produce from burning fossil fuels, and we will still be producing carbon dioxide from burning fossil fuels to 2100 and beyond, with the carbon dioxide we capture and dispose of permanently back underground. The catch, of course, is this is expensive. At that rate, just the sort of mid-range scenario for disposing of carbon dioxide in the middle of this century, we would be spending $1 to $3 trillion a year alone on carbon dioxide disposal, sticking carbon dioxide back into the Earth's crust. It's an expensive thing to do. And in context, the Brits present will sort of may remember this incident a few years ago. If you just work out the UK's share of the carbon dioxide disposal challenge in 2050, it adds up to about £350 million a week. Now, this was the number they put on the side of the bus to convince us to leave the European Union. And I can assure you that the benefits of membership of the European Union would have been a lot more tangible to the British voting public than the benefits of a carbon dioxide disposal program. So we have a problem at the moment that although people acknowledge, yes, we need carbon dioxide disposal, oh, well, I suppose the government will pay for it. Will it? We need other ways of thinking about climate policy. Yes?
So I work in the sanitation space in India, and we are also looking at circular technologies. My question to you is, in the slide before, when you were talking about solutions, are there ways to bundle some of the solutions when you look at carbon dioxide?
Yes, there absolutely are, and I'm just coming to them. So that's a great question because it cues up the rest of this lecture. Okay, so how do we get to geological net zero? What's the sort of most defensible, what's a defensible pathway to it? And the difficulty with it, I pressed it, is that if we look at these scenarios and we try and sort of read off what companies should do from them, and there's a whole game doing this. The Science Based Targets Initiative issues lots of guidance to companies on if you want to be aligned with 1.5 degree scenarios, this is what you have to do. You have to reduce your this, that, and the other, and so on. And you can imagine company directors looking at these and thinking, well, it looks a bit like Wile E. Coyote, who's just running along and then sort of goes off a cliff and, collapses. It just doesn't make, the scenarios themselves don't look realistic. So how can you, as a realistic CEO, no CEO would want to be an unrealistic CEO, how do you align yourself with something that doesn't itself look like a realistic prediction of what is going to happen? So what can we use these scenarios for if we don't sort of immediately believe them as what the world is going to do over the next few decades? Well, we can look at what's underlying them. What's driving the transition? How can we understand what's happening in these scenarios by just looking at what happens between the red and the blue lines? So this is introducing something you may not have come across, but called the net geological carbon intensity of the fossil fuels we still use. And this is the fraction of carbon dioxide that's generated by burning those fossil fuels, not the emitted, but the fraction of the carbon dioxide that's generated by the burning of fossil fuels that is left above ground, that is not captured and re-injected back into the Earth's surface. So right now, that fraction is 1. We leave it all above ground. Well, 99.9%, okay? And we know, to get to geological net zero, we need to reduce that fraction to 0. And you can see that's what happens. Here this is 1 minus the blue over the red, which, as everybody knows, makes purple. These are the lines which show you that ratio in these scenarios, and you can see they all head towards 0. They head towards 0 is still a bit of a sort of spaghetti. There's still a bit of a mess, so it'd be quite difficult to look at those and say, I need to be at a certain point in 2040. You could say, well, we could be all over the place in 2040. So that's not very helpful, is it? But wait a minute, they all start declining at different times. So if I correct for that, if I just slide them around left, right, so they all reach 5% at the same point, then, well, they certainly start to tidy up a bit. And then you'll notice they're still fanning out at the end because they're all reaching net zero, geological net zero, at different times too. So we can correct for that as well by, instead of plotting against year, we plot against time remaining to net zero. Yeah? And suddenly, from this whole spaghetti of scenarios you started with, it's almost like you've uncooked the spaghetti and it's come out nice and straight and stiff the way it came from the shop. And in fact, it's shown up a shape that's exactly what you'd predict if you were a physicist saying, how do you get from A to B in the shortest, in the sort of, as it were, the lowest energy pathway, what we physicists like to call a geodesic. Okay, if I was to throw this off the dice, I'm not going to do it, it would follow a parabolic path down to the ground because it's following the lowest energy path, and the lowest energy path for the global economy to get us to geological net zero is to start where we are now and follow a quadratic. I told you there was only one bit of maths in this lecture, but here it's come again. Maths is useful. It follows a quadratic curve down to 0. So we know what it takes to stop fossil fuels from causing global warming. If we want to do that by 2050, we need 4% capture by 2030, 16% by 2035, 36% by 2040, 64% by 2045. You can see what I'm doing. I'm just squaring the numbers as I go up. And finally, 100% by 2050. It's that simple. If we don't do it 100% by 2050, if we do it 100% by 2060, it just means we're going to end up a bit warmer. We still got to get there, because one day, as I said at the beginning, we are going to stop global warming. Now, the exciting thing about this is, for Britain at least, we could be at 4% by 2030 with the projects that this government is now investing in Teesside and Merseyside. We are starting finally, having gone on and on and on about it for 20 years, we are finally starting to re-inject carbon dioxide back under the North Sea. To get all the way to 100%, we need to go further, and we need to start recapturing carbon dioxide back out of the atmosphere. And this is a plant that's being completed in Texas to do just that. That, of course, is a much more expensive operation. But this is what happens in the scenarios. This is how, in the scenarios where we meet the goals of the Paris Climate Agreement, we stop fossil fuels from causing global warming in the second half of this century. And by the way, I know those thinking about this project in Texas, the ownership of that project is particularly interesting. One of these chief executives has a plan to stop the fuels they sell from causing global warming by 2050. It's a plan, not a commitment, I should say. So any prizes for guessing which it is? They're also unusual in one other way as well. Yeah, Vicky Holub is the only CEO of any oil and gas company in the world who happens to be a woman. Occidental are also the only oil and gas company in the world that happens to have a plan to achieve geological net zero. There is a catch, though. Vicky Holub is the CEO of a shareholder-owned company. She has to keep her company profitable, and we still really haven't worked out how to pay for geological disposal. So that's the big policy question that I'm going to end on. And I'm probably going to overrun. How much can I mean, there have been a certain amount of questions as we went along. Okay. Because it's a really, really important question. How do we pay the bill for geological carbon dioxide disposal? At the moment, it's paid for by government subsidy. Here in the UK, it's effectively a direct subsidy from government. They dress it up as something called a contract for difference or regulated asset base. But in the end, it's the taxpayer who forks out and takes the risk. In the US, under the last administration, they introduced something called a 45Q tax credit. Its status is sort of wobbly at the moment, but it seems to be continuing. It illustrates the danger of relying on the transition in policies in the US illustrates the danger of relying on government handouts to pay for this kind of thing, as the next government can just decide, no, we don't want to do that. So and the other problem with government handouts is they're extremely inefficient at discovering what things actually cost. If you ask an industry, how much do you need to get rid of your carbon dioxide, they're bound to say, a lot of money. And they also involve a big drain on public finances, which of course we don't have at the moment. So the big question I want to ask you is, how can we make carbon dioxide disposal, and this is where I think the question on the circular economy and other waste disposal challenges was particularly welcome. How can we make it become something other than a low-margin, subsidy-driven public service? And the answer, actually, I think, is exactly what you suggested in your question implicitly, which is to bundle the obligation to get rid of carbon dioxide in with the benefits of generating it in the first place. So just to illustrate the idea, this is where we are now. This is a sort of schematic of the carbon economy. We have the blue arrows show either actual or embedded carbon dioxide coming into the economy in the form of fossil fuels by an extractor or an importer of oil, gas, or coal. They pass those fuels on to industry who make products that go to consumers, and it all ends up in the atmosphere. So what's happening? Well, at the moment, the only entity in this economy that's really affected by climate policy is the industrial point sources. They're in Europe and UK, at least, they're being subject to a substantial carbon price through various mechanisms. So they're grumpy and thinking of moving to Malaysia or places where they think they might get a lower carbon price. Consumers are generally confused about how climate policy is working. The atmosphere is sweating. Over here, we have a geological storage operator. This is somebody who set up a business to put carbon dioxide back underground. But as you can see, they're sad and lonely because there are no arrows pointing towards them. Nobody has any real incentive to avail themselves of their services. The government is fast asleep, and the extractor importer is laughing all the way to the bank. So what can we do to change this? Well, the current UK funding model is to throw lots of money at the geological storage operator, taxpayer subsidies, who would then acquire carbon dioxide from the industrial point source. So probably some of the money flows through to the industrial point source. That makes them happy, but it makes the government cross because it's having to spend all this money. Probably makes consumers cross too because they're the ones paying the taxes. And why should we be spending all this money on this highly profitable industry anyway? Because, of course, the geological storage operator is almost certainly a division of a fossil fuel company in the first place. And the atmosphere is still sweating because most of the carbon dioxide is still going back in the atmosphere anyway. And the extractor importer is still laughing. That goes without saying. There's another idea. We impose a requirement on the industry to get rid of its carbon dioxide. There's a lot of enthusiasm for this sort of thing. Just regulate industry to make it get rid of its carbon dioxide. The result is you end up with an industry that's very cross and thinking of moving even faster away from whatever jurisdiction is imposing climate policy. We have a real problem at the moment that climate policies tend to push carbon-generating activities away into regions with weaker climate policies. If you think about the world as a whole, what we need is to crowd carbon dioxide generating activities into regions that have stringent climate policies, because that's where we need to generate the carbon dioxide. And yet the vast bulk of climate policy does exactly the opposite. And a real challenge for you is to try to work out how can you craft a climate policy that actually would make Europe or Canada or Australia or whatever country is implementing this climate policy a more attractive place to generate carbon dioxide than a less one. I'm going to tell you a suggestion for this, but I think you should also think of your own suggestions as well, because because this is one of the big challenges we face. My suggestion, and something we've been advocating for a while now, is something called a carbon takeback obligation, inspired directly by the kind of obligations placed on waste disposal in circular economy measures that you were referring to earlier on. So what happens is the government requires, green arrows here show sort of compliance requirements. The government requires the geological storage operator, the government requires the extractor importer of fossil fuels. Anybody who wants to sell fossil fuels in the economy is required to produce some evidence, a carbon storage unit, a certificate of some sort, to say that a certain fraction of the carbon dioxide that those fossil fuels will generate has been captured and securely disposed of back underground. So the geological storage operator generates these carbon storage units, sells them to the extractor importer, or perhaps more likely, they are different divisions of the same company, in order for them to carry on selling their fossil fuels. What happens? Well, the industrial point source suddenly discovers they can sell their carbon dioxide. Carbon dioxide becomes valuable as opposed to a pain. So they're perhaps intrigued. Consumers would still be confused. That's a fairly safe bet. But also the impact of this small obligation on the industry to get rid of carbon dioxide wouldn't actually feed through into any significant impact on consumer prices. So it's something you could introduce gradually over time without the public getting immediately upset about it. The atmosphere is still sweating. We haven't made any difference to the amount going into the atmosphere, but the geological storage operator at least is happy because they have a business, and the government has its nerd glasses on because it's learning how to do it, how to monitor, report, and verify this whole process. And the extractor importer is probably rather cross because they now have an expense that they didn't have before. I described this to a senior executive from ExxonMobil. I'm not shy about naming names here, a couple of years ago. And he listened carefully and he said, yeah, no. We got to work on it. As we scale over time, we scale up that stored fraction. We draw down the net geological carbon intensity of the fossil fuels passing through the economy. We'll get to a point where the geological storage operator starts to run out of carbon dioxide. They've hoovered up all the available, accessible carbon dioxide that's being generated by cement plants and steel factories and whatever remaining power stations are still using fossil fuels. And so they actually have to resort to, and that's a good problem to have. We want industry to be out there searching for carbon dioxide, not sort of avoiding it as hard as they can. And so you have a new element here, those fans there, that's a direct air capture operator. That's somebody who's actually taking carbon dioxide back out of the atmosphere. By this time, carbon dioxide has become really valuable because it's expensive to take it back out of the atmosphere. So point sources of CO2 would be making a lot of money out of their carbon dioxide. Very different from what their carbon dioxide is costing them at the moment. Consumers are still confused, that's for sure. The atmosphere is feeling perhaps a little bit better because the flow of carbon dioxide into the atmosphere is slowing down. The geological storage operator is now making serious money. The government's still learning what to do. And the extractor importer is perhaps seeing that this could work out for them not quite as badly as they first thought. Finally, we get to 100% net zero, geological net zero. As achieved by, you'll notice the thickness of the arrows, the blue arrows denote the amount of carbon dioxide. So notice there's now as much going back underground through the geological storage operator as is coming in from the extractor importer. You'll notice the economy as a whole is using less fossil fuels. Of course, if you include the cost of disposing of the carbon dioxide into the cost of using fossil fuels, then we will definitely use less of them, but we probably won't use zero. So, what happens? Well, the industrial point source is happy, no longer thinking of moving to China because they can sell their CO2. They don't have to pay for it. Consumers are happy because we stopped global warming. The atmosphere is breathing a sigh of relief. The geological storage operator is still making loads of money. The government's feeling awesome because we finally found a climate policy that works, and the extractor importer has saved the planet. The surprising thing about this is it's totally affordable. If we look at what carbon capture costs today from a clean point source like a refinery or an ammonia plant, all you have to do is compress it, liquefy it, and stick it back underground. $50 a ton will do it. If you have to recapture it out of the atmosphere and you've got 30 years of technology development, they can probably get that to $250 a ton. At the moment, if you had to pay Oxy to do it for you, you'd be paying north of $600 a ton. And if you had to pay Climeworks to do it for you, you'd be paying north of $1,000 a ton. So it's nascent technology, but these are first-of-a-kind plants, and the people who work on that Stratos plant in Texas are very confident that as they roll these plants out, should they get the right policy environment to allow them to do so, they'll be able to get costs down. And, you know, getting costs down by at least a factor of 2 from your first-of-a-kind is normally, you know, a relatively easy lift for an industry. Okay, so that's what that's the red line there, the actual cost of capturing carbon dioxide through the transition. Of course, because we only require a certain fraction to be captured, the actual impact on the fossil fuel consumer is much less, because you start off only requiring a small percentage to be captured and stored. In fact, even by 2040, the stored fraction is only 36%. Remember that curve and the way the geological carbon intensity of our continued fossil fuel use has to fall over time in order to achieve geological net zero. So capturing and storing 36% of the carbon dioxide generated by continued fossil fuel use in an advanced economy like Europe or the UK would cost probably less than $50 a ton, less than what we currently pay in carbon taxes. And if we look at it in the context of historical fuel price fluctuations, it's even more striking. That's what that looks like over the past 25 years. 60 pence on a litre of petrol. If our Tony had decided he wanted to stop fossil fuels from causing global warming within a generation, he could have done it by now. The technology's been there all along. We just haven't had the policies to make it happen. So to sum up, we need to stop fossil fuels from causing global warming. That, you'd say, is obvious. We need to do it before the world stops using fossil fuels. That may feel discordant to you, but it's true. And you've got to think through the implications. Halting global warming requires 1 ton of carbon dioxide safely and permanently disposed of for every ton still generated by burning fossil fuels in the 2050s. So we need a credible CO2 disposal plan that applies to all emissions, including Scope 3, so including the emissions resulting from the products companies sell, and aiming for 10% by 2035 and 100% by 2050 would be a great start. A long time ago, I quoted Sultan al-Jaber earlier on. I'm going to end by quoting another oil minister from that part of the world, the Saudi oil minister, Sheikh Yamani, from the 1970s. And he loved to say that the Stone Age ended before we ran out of stones, and the oil age will end before we run out of oil. And I'd like you to remember that global warming must end before we stop using fossil fuels. And I hope that's given you some things to think about. Thank you.